A great day to one and all. I am Mr. Ensho, and today I will be discussing with you probability problems related to permutations and combinations and on how we can solve them. But before we dig into this, it is necessary for us to review the concepts of probability. When we speak about probability, let's denote it by P of E. It refers to the likelihood of a certain event to occur. And the value of P of E actually ranges from 0 to 1. A probability of 0 tells us that a certain event is impossible to happen, whereas a probability of 1 tells us that a certain event will surely happen. As the value of probability approaches 0, the lesser the likelihood of a certain event to occur, and the nearer it is to 1, the more probable it will happen. And we have different types of probability, but for now, I will be tackling classical probability. And classical probability is defined as the number of favorable outcomes divided by the total number of outcomes. So in here, it is important that we determine how many outcomes are in favor of a certain event, and you take that as a ratio together with the total number of outcomes. And to determine the total number of outcomes, there are many ways, depending on the situation. And if P of E refers to the classical probability of an event to occur, then we have the probability of the complement of E, which is in fact the probability that that event will not occur. And let's call it P prime of E. And that is defined as simply the difference of 1, which is the maximum probability that a certain event will occur, minus the probability that it will happen. And also, if you manipulate this equation, you could see that if you add P of E both sides, then P of E plus P prime of E is equal to 1. That is, the probability that it will happen plus the probability that it will not happen will always add up to 1. So those are simple review. That's something we have to recall. And this time, we will be tackling some of these problems. Probability problems related to permutations and combinations. Let us start with an easy one to illustrate the given. Directions. Answer the following as required. Show solutions. Express all probabilities as fractions in simplest form. Probability could be expressed as decimal or percent, but for now, we will have it in fraction form. Let's have the first one. A 6-sided fair die with numbered 1, 2, 3, 4, 5, 6 is tossed. What is the probability that a prime number comes out? So for the solution of this, by the way, before I move on, feel free to pause the video from time to time. You may solve the problem on your own and check if you have the same answer as what I did. From here, a die has 6 possible outcomes, 1, 2, 3, 4, 5, and 6. And when we speak about a prime number, these are natural numbers greater than or equal to 2 that have exactly 2 positive factors, 1 and itself. And if you could see, there are 3 prime numbers out of this 6. We have 2, 3, and 5. We could see that 2 has only 2 factors, 1 and 2. For 3, it's 1 and 3. And for 5, that's 1 and 5. And since there are 3 out of 6, or there are 3 favorable outcomes out of the 6 possible outcomes, then the probability of a prime to come out is, let's denote it by P of prime, is equal to the total number of favorable outcomes 3 all over the total number of outcomes, which is 6. And if you simplify 3, 6, that would be 1/2. I hope you got this correctly to start with, because as we progress, some of the problems actually or gradually increase in terms of difficulty. Let's have the second problem. 2 coins are tossed at once. What is the probability of having no heads, having exactly 1 head, and having 2 heads? So what do you think? Remember, if you toss a coin, it has 2 possible outcomes per coin. That's a head or a tail. And by utilizing our fundamental counting principle, the first slot is for the first coin and the second slot is for the second coin. The first coin can have 2 possible outcomes, head and tail. Also, the same is true with the second coin. And by the fundamental counting principle, we have to multiply them to determine the total number of outcomes. So that's 2 times 2 or 4 outcomes. And what are those 4 outcomes? These are head, 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 tail, tail, head, and tail, tail. So from here, let's have letter A. It says here, no heads. And if there is no head, so that means that all are tails. And how many have no head? So it's just this one. And that's 1 out of 4. And that the probability that no head occurs is 1/4. 1/4 is already in simplest form. How about having exactly 1 head? So how many here? So we have 2. We have head, tail, and tail, head. So that's 2 out of the 4 outcomes. And that is the probability of having exactly 1 head is 2 over 4. And dividing both numerator and denominator with their GCF, which is 2, we have 1/2. So the probability or the chance of having exactly 1 head is 1/2. How about letter C, having 2 heads? So that's this one, right? It's only 1 out of the 4. So the probability of having 2 heads is still 1 over 4 or 1/4. I hope you got this correctly as well. And if you did, congratulations. But if not, better practice, more problems. Let's have the third one. 5 friends, Annie, Bea, Cathy, Dea, and Elsa, would like to occupy a row of 5 chairs. Let's have the letter A. In how many ways can they sit in all? So this is a permutation problem because order here doesn't matter. And besides, we could also utilize the fundamental counting principle without repetition here. So there are no restrictions. This means that any person could sit any of these 5 chairs, in any of these 5 chairs. So that would be 5 factorial, or the first person. In the first seat, 5 people could sit there. In the second seat, only 4 could sit. Since the first 2 have already occupied the seats, then there are 3 more for the third seat, then 2 more for the fourth seat, and 1 more for the last seat. And that is 120. So there are 120 ways for these 5 people to sit in all. But how about letter B? In how many ways can Annie and Bea be seated next to each other? So This time, there is now a restriction. Cathy, Dea, Elsa could sit anywhere as long as Annie and Bea are seated next to each other or they are adjacent to one another. And that no person should be between Ana and Bea. So for such, let's do the slot method thing. So I have here A, B, C, D, and E. But since Ana and Bea are together, I counted them as one slot. So you see, I have here only, I underlined them once. And C, D, and E are treated as one slot each. And how many slots do you see? We have 1, 2, 3, 4. That is why we have 4 factorial ways because we have 1, 2, 3, 4. But there are 2 people, Ana and Bea, who could interchange seats as long as they are together. Hence, they could still arrange themselves in 2 factorial ways. Hence, for Ana and Bea to be seated next to each other, there are 4 factorial times 2 factorial ways in all. 4 factorial means 4 times 3 times 2 times 1 or 24. 2 factorial means 2 times 1, which is 2. So 24 times 2, we have 48. 48 ways for Ana and Bea be seated next to each other. I hope you got this as well. Now, how about letter C? Letter C now asks something in relation to your answers in A and B. We could utilize the answers in A and B to answer letters as such. That is, what is the probability that Ana and Bea are seated next to each other? So, Ana and Bea can be seated next to each other in 48 out of 120 ways. 48, this was computed in based on our computation in letter B earlier. Out of the total 5 factorial or 120 ways in all. And since 48 are favorable out of the 120 ways in all, then the probability that A and B seated next to each other is 48 out of 120, and dividing both numerator and denominator by their GCF, which is 24, we have 2/5. I hope you got 2/5 correctly as well. Let's have letter D. How about, in how many ways can Ana and Bea be seated not next to each other? In letter C, next to each other. But for letter D, not next to each other. So to do this, there are 120 ways to occupy the 5 seats, of which Ana and Bea can be seated next to each other in 48 ways, based on our solvings in A and B. Thus, to determine the ways that they are not together or seated next to each other, we have to subtract. There are 120 minus 48 or 72 ways that Ana and Bea be seated not next to each other. I hope you got this. And how about for letter E? What's the probability now? That Ana and Bea are seated not next to each other. So based on this one, on the one we did on letter D, there are 72 ways that Ana and Bea be seated not next to each other. And since there are 120 ways to occupy all of those seats, then the number of favorable outcomes for not next to each other is 72 all over 120, which is the total. And dividing both by 24, we get 3/5. But there is another way. And what is that way? Remember the complement rule. If the probability that they are seated together is P of E, then the probability that they are not seated together is P prime of E, or you subtract it from 1. That is, we have 1 minus that they are seated together as 2/5 earlier, and that is 3/5. So you see, I was able to solve this problem using 2 ways, and in your actual solution, you could choose any of these. All right, so far, so good. I hope you understand it. Number 4. Andy plans to arrange 3 different mathematics, 2 different science, and 4 different English books by stacking them in a pile. In how many ways can the books be arranged in all? So this one is a bit simple. There's no restriction about the arrangement of the books. We could see that there are 9 books in all. That's 3 plus 2 plus 4, which is 9 different books in all. They can be arranged in 9 factorial ways, which means 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And using your calculators, that's 362,880 ways in all. So that's for letter A, without restrictions. But how about if we put restrictions now? Let's go to letter B. So what is the probability that all math books are together? So for the solution of this, take note, if this is the case, you could place them in any way that you like, as long as all math books are together. No other book, no science, no English book is between any 2 math books. So from here, I made this bold. We have here M1, M2, M3 to represent the 3 different math, S1, S2 as the 2 different science books, and E1, E2, E3, E4 as the 4 different English books. Now, I made this bold to emphasize that you take them as 1 slot because they're together. And so how many slots are there? That's 1, 2, 3, 4, 5, 6, 7 slots in all. So that's 7 factorial ways. However, these 3 math books could still be arranged among themselves as long as they are together. That's why these 3 math books could be arranged in 3 factorial ways. 7 factorial, or 7 times 6 times 5 times 4 times 3 times 2 times 1 is 5,040. 3 factorial, or 3 times 2 times 1 is 6. And their product is 30,240, which is the number of ways for all the math books to be together. I hope you got it. And but the thing is, we are not yet done because the problem is asking for probability. Based on our answer in A, there are 9 factorial ways in all that you could arrange them. And there are 30,240 or 7 factorial, 3 factorial ways in all, that in such a way that all math books are together. So the probability is 7 factorial, 3 factorial all over 9 factorial. Or that's, if you wish, you could utilize their simplified value in standard form, the 30,400 divided by the value of 9 factorial. 7 factorial times the 3 factorial becomes 3 times 2 times 1 or 6. The 9 factorial, I made it 9 times 8 times 7 factorial with the intention of canceling the 7 factorials. And what is left is 6 over 72, which when simplified is 1/12. So the probability that all math books are together is 1/12. I hope you got it. And if you did, great job. Letter C. How about what is the probability that books of the same subject are not together? Meaning to say, all math books are not together, the science books are not together, and the English books are not together as well. So to do this, it is important to calculate first the total number of ways that they can be together. And to accomplish that, we have here the 3 math, the 2 science, and the 4 and the 3 and the 4 English. So we treat them as 1 because they're together. This is 1, 2, 3. So our n is 3. That's why I have here with me my 3 factorial. These 3 math books could be arranged in 3 factorial ways among themselves. These 2 science in 2 factorial ways. And these 4 English books in 4 factorial ways. When simplified, we have 6 times 6 times 2 times the 4 factorial is 24. And that gives us 1,728 ways for all the books of the same subject to be together. However, we are after of the not together. So for such, remember that there are 362,880 ways in all to arrange all of these books. And that there are 362,880 minus 1,728 or 361,152 ways that books of the same subject are not together. For this case, even though all the books are together, for example, we have E1, E2, E3, E4, if there is at least one that's between any 2 English books, then if there is any other subject that is between the 2 English books, then that is already an arrangement that satisfies the given. So from here, the total is 362,880. So that's the favorable is 361,152 all over the total, which is 362,880. And if you simplify this, that would be 209 over 210. All right. I hope you are doing well, my friends. Let's have the next number. Let's have number 5. All 5-digit numbers are formed using the digits 1, 2, 3, 4, and 5, and repetition is allowed. That is, for example, 1 could be repeated. You could have it twice, thrice, 4 times, 5 times. The same is true with the other letters or the other digits. Micaela wrote a random number using these digits. What is the probability that the number is even? So you could now apply here the slot method and the fundamental counting principle. That is, by the fundamental counting principle, we have here the 10,000s place, 10,000s, thousands, hundreds, tens, ones. And that since repetition is allowed, then you could have 5. You could use any of these 5 digits in any position. And hence, you will have 5 times 5 times 5 times 5, or that's 5 to the 5th, or 3,125 5-digit numbers with repetition using 1, 2, 3, 4, and 5. However, for the even, you could have all the digits, the same digits in the 10,000s, thousands, hundreds, and tens. However, for a number to be even, the ones digits should be an even digit. Hence, for the ones place, it could either be 2 or 4. That's why there are 2 possible outcomes for the ones place. And by the fundamental counting principle, multiplying them, we have 1,250 5-digit even numbers, utilizing only 1, 2, 3, 4, and 5 with repetition. And this is the number of favorable outcomes out of the 3, 1, 2, 5. And so if you wish, you could divide 1 to 50 directly by 3, 1, 2, 5. Or in my case, I use their factored form because if you could see, you will divide the 5s, 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 5s. And what is left in the numerator is 2, and in the denominator is 5. And so the probability that the number Micaela wrote is even is 2/5. Okay. Number 6. 5 coins are tossed simultaneously. What is the probability that at least 3 heads come out? So in this particular problem, this now involves combination because the order here does not matter. And by the fundamental counting principle, the first coin has 2 outcomes, second coin 2 outcomes, third coin 2, fourth coin 2, fifth coin 2. And multiplying them, you have 2 to the fifth, or that's 32 possible outcomes in all. However, if you have at least 3 heads, then the minimum number of heads that come out is 3. So there are 3 favorable cases for such. Your case 1 is 3 heads and 2 tails. Case 2 is 4 heads, 1 tail. And case 3 is 5 heads and that you have no tail. So we will have the combination of each. From here, let's take case 1, 3 heads and 2 tails. So out of the 5 coins, if 3 are heads, so we have 5C3, and the remaining 2 coins should turn out tails. So that's 2C2. But you may disregard the 2C2 because if the n is just equal to r, then its value is just 1. So 5C3 becomes 5 factorial all over 5 minus 3 factorial, 3 factorial. The 2C2 becomes 2 factorial all over 2 minus 2 quantity factorial times 2 factorial. Here simplifies to 1. The first one, I represented the 5 factorial as 5 times 4 times 3 factorial with the intention to cancel the 3 factorial. The 5 minus 3 quantity factorial becomes 2 factorial or simply 2. And what is left here is 5 times 4, 10 divided by 20 divided by 2, which is 10. Here, it's just 1. So that's 10. There are 10 ways for 3 heads, for exactly 3 heads to come out of the 5 coins that you tossed. Let's have the second case. And using a similar reasoning, if 4 are heads and 1 is a tail, then out of 5, you have 4 heads. So that's 5C4. And the remaining 1 coin will be tail for sure. So 5C4, it's 5 factorial all over 5 minus 4 quantity factorial times 4 factorial times 1C1, which is 1 factorial all over 1 minus 1 quantity factorial 1 factorial. The first factorial there, the 5 factorial, could be expressed as 5 times 4 factorial with the intention to cancel this. And 5 minus 4 is 1, then 1 factorial is just 1. So this becomes 5 here, and this becomes 1. So that's 5 times 1 or 5. So there are 5 possibilities or possible outcomes for 4 heads to exactly come out. And for the third case, if you have 5 heads and 0 tail or no tails. So out of the 5 coins, so 5 are heads, so that's 5C5. And of course, 0, there's none left, so 0, combination 0. So 0C0 is just 1 for sure. The 5C5 is 5 factorial all over 5 minus 5 quantity factorial 5 factorial. And 5 factorial over 5 factorial is just 1. 0 factorial is also 1. So we have 1 times 1, which is 1. So what do we do then with 10, 5, and 1? Since we have 3 separate cases, then it is important to determine the total number of cases through addition. There are 10 plus 5 plus 1 or 16 possibilities to have at least 3 heads. And remember, there are 32 possible outcomes in all. So that's 6. The probability of having at least 3 heads is 16 over 32 or 1/2. If you got it correctly, great job. But if not, still keep on going. Let's have number 7. 5 students from SPSTE and 7 students from STVEP are being eyed as contestants for Sayawit. if the official entry of the school should have 6 members only, what is the probability that exactly 3 of them are from SPSTE? So if 3 of them are from SPSTE, then remember there are 6, no? Then that 6 minus 3 equals 3. We should also be taking 3 from STBEP. Hence, this is the total number of ways to select them is, but before that, we will choose 6 out of 5 plus 7 or 12 students. So you will choose 6 out of 12. So that's 12 combination 6. And I have, by using the combination formula, we have 12 factorial all over 12 minus 6 quantity factorial times 6 factorial. And this simplifies to 12 factorial all over 6 factorial, 6 factorial. You could simplify this using your calculators, or you could do this manually. It's your choice. And simplifying such gives you 924. So that is, there are 924 ways to choose any 6 out of the 12 students without restriction. But remember, as what I mentioned earlier, if 3 are from SPSTE, then 3 also will be taken from STBEP because you have only 6 contestants or 6 members. So there are 5 SPSTE, so that's 5 C3 ways to get the students from them, and 7 C3 ways to get the 3 out of the 7 STBEP students. Simplifying each factorial or by substitution to the equation, to the combination formula, we have 5 factorial all over 5 minus 3 quantity factorial 3 factorial times, for the second one, 7 factorial all over 7 minus 3 quantity factorial 3 factorial. And with that, we have here the first one becomes 5 times 4 times 3 factorial all over. This one is 2 times 3 factorial. This will cancel. For the second one, this will become 4 factorial here. That's why the 7 factorial here on top becomes 7 times 6 times 5 times 4 factorial, with the intention to cancel the 4 factorials or to divide them into 1 to become 1. And the 3 factorial here is just 3 times 2 times 1 or 6. From the first one, we have 5 times 4, that's 20 divided by 2 or 10. For the second one, the 6 and the 4 factorials would cancel. So 7 times 5 or 35 will be left. And the total number of ways to choose 3 from SPSTE and 3 from STBEP, it's 350 ways. But remember, there are 350 ways that are favorable for this condition out of the 924. So that's 350 over 924, or 25 over 66. That is the probability of selecting 3 SPSTE and 3 STBEP learners. I hope you got this. And if you have questions or clarifications, please feel free to reach me in my social media accounts. Feel free also to comment in the chat box or in the comment section. And I wish you all the best. God bless everyone, and a great day to one and all.